Problem number 5 asks, indicate the best method and or identities to use when evaluating this integral. And it gives you e to the 2x cosine cubed of e to the 2x all times dx. So this is kind of a tricky question because it says indicate the best method. It might not be the method that you want to use, but it is the best method for solving it. So we have 5 different options. The first thing I notice about all those options on the exam is that they all start with the u substitution. So let's see if there's some kind of u substitution we can make to validate that. If we can't find a u substitution to make, it automatically makes it letter D, which saves us a lot of time. So if we start with the u sub, if we are somehow able to eliminate it, we've already answered the question. So when I look at these kind of terms, I notice there's an e to the 2x and an e to the 2x in here. Now whenever I have like a cosine cubed or a natural log term, trying to substitute for what's inside sometimes makes your life a lot easier, and it's usually a good place to start. So if I have u equals e to the 2x, can I even make a substitution using this? Well, this tells me that my derivative needs to be 2e to the 2x dx. Now I don't have it 2e to the 2x, but I do have it e to the 2x. And I have this 2 here, but I can account for that by just dividing it over to the other side. So this tells me that du over 2 is equivalent to e to the 2x dx. So I can make this substitution for a u sub. So if I go ahead and plug that in, I have cosine cubed u du, and what I'm going to do is I'm going to write the 1/2 out front here. This is a constant. So u substitution does in fact work, and it looks like it makes it a lot easier to manage than doing integration by parts. So letter D is already pretty much crossed off. So I'll go ahead and write A, B, C, D, and E. So we've already crossed off D. We have 4 more options to try to figure out. So I noticed that 2 of them, A and C, both involve using the double angle formula, or half angle formula, which is sine squared. So sine squared theta equals 1/2 1 minus cosine 2 theta, and the equivalent one for cosine squared, which is just the same thing but with a plus in the middle. That's still 1 plus cosine 2 theta over 2. When I see this, if I try plugging in something like that in here, I end up with something that's really weird. So for one thing, I can't even use this one. I would have to use the cosine squared one because there aren't any sine squares. So if I go ahead and try to do that, what I end up with is I end up with kind of a mishmash of cosine cubed times cosine 2 theta. And from there, I don't really have any other way to sub in for that extra cosine of u. So using identities like these, you want to be careful. If this was just cosine squared, that actually would work pretty well, because then I could just convert it, and I'll go ahead and just write it down anyway, just for the sake of completion. 1 plus cosine 2 theta. If I go ahead and write that down, if it's just cosine squared theta, if I plug this in, it actually becomes a pretty easy integral to solve. I have a 1/2 out front, I can pull the 1/2 out. I'm just integrating 1 plus cosine 2 theta, which I can do by just going straight across because it's separated by a plus in the middle of the terms. So this would just be theta, and this would be sine 2 theta over 2. So I could integrate that, but in this case with a cosine cubed, it doesn't really work that well. So I'm going to go ahead and cross these off. We don't want to use these, and that also eliminates A and C. So we've kind of come to a point where if we wanted to, we could make a guess, and we'd have a 50% chance to get it right. Well, we want a 100% chance to get it right. So by looking at the other 2 options, B and E, I have u sub and integration by parts, and I have u sub and sine squared plus cosine squared equals 1, so using the trig identity. Now with these kind of terms, if I try to use integration by parts, what would my terms have to be? Well, in this case, I don't really see 2 terms that I could plug in. I guess I could if I really wanted to, but this would have to be my u term, And this would have to be my dv term, because I can't derive du. I have to have like an x term, or I would have to have like a u term in here. So if it was u times cosine cubed of u, then integration by parts would work really well. But in this case, because I'm missing an extra u term, integration by parts doesn't really work so well. If I try to derive this term out, it's just going to become more and more complicated over time, and we're not really going to arrive at an answer. So what that kind of leaves me with is, if I eliminate the integration by parts answer, I'm left with letter E. Letter E says that using sine squared plus cosine squared equals 1 can solve this integral. And it can. So if I go ahead and plug in something like that, so if I have sine squared u plus cosine squared u equals 1, I would have to substitute in for a cosine squared. If I go ahead and write that out, I end up with 1 minus sine squared u cosine of u du. This is now just an additional substitution, so I can do like v and dv or something like that, with v equal to sine and dv equal to cosine, which just becomes like an easy 1 minus u squared term to solve. So in this case, using this identity is in fact the best way to solve this. So letter E for number 5 is the final answer.
The Teaching Center, UF's Learning Resource Center.